So I'm moving on to alkenes. I'm done with alkenes. So in our studies or in these recordings, I'm going to majorly focus on synthesis, call it lab preparation. Then let me write it here. So I'm going to focus on synthesis, and reactions. These areas are of greater importance. These ones are high yield. They are high yield areas. So I'm going to first focus on that. And I want you to first master the synthesis and the reactions. Then later on, I will make a recording. I will make a recording for the isomerism. So I'm going to be skipping these things, but I will compile them in one lesson. Isomerism and the other thing is the physical properties. So physical properties, and you realize that I'm not going into details of nomenclature because with this nomenclature or naming, you may call it naming, you realize that when I mention a name in our synthesis, I'm going to be throwing more hints about the name word, the positions. So I'm going to try to bring in nomenclature within our synthesis and the reactions such that the whole thing moves on very quickly. I don't want us to delay. I don't want us to delay on one thing. Then maybe the other thing I'm going to be talking about, mechanisms. So I'm going to be talking about mechanisms there. So those are the areas of greater importance: mechanisms, reactions, synthesis. After covering that, I will make one video having all these things covered. We shall cover them. We shall cover them next. So our aim is covering these alkenes. Then I move on to alkynes. After alkynes, then the first part will be done. But let us move on to the lab preparations. So from our alkenes, first we have to understand the general formula. CN H2N, like that. So every alkene that I'm going to be mentioning is going to be following that general formula. Then the other thing you have to know is that these alkenes are having double bonds. Somewhere within the chain there is a double bond that makes it an alkene. Then take note of this prefix. At first we had the alkane, but now we've removed this, we've removed that part and established another prefix there. It's called a suffix here. So that is it. Then the other thing we have to maybe mention, I said isomerisms, we shall cover them later. Physical properties. By the way, physical properties, you can even read them. Physical properties are the same as those of, they are a bit similar. They're a bit similar to those of alkenes. So, but anyway, as you read through, such that by the time you come, you're also well conversant with the thing. So I'm going to preparations straight, and under our preparations, call it the lab prep or lab preparation. The first one is going to be preparation from acid catalyzed hydrolysis of alcohols. So I'm going to label it. This is, let me see, from alcohols. So preparation from alcohols is going to have so first you have to understand, okay, these things we shall have a separate lesson for alcohols, but what you have to know is that in alcohols we have primary alcohols, we have secondary alcohols, and tertiary alcohols. So from primary alcohols, preparation from primary alcohols. 1. we can have an example of a primary alcohol, which is CH3CH2OH, and we shall call it ethanol. So from ethanol, when you add in concentrated sulfuric acid at 180 degrees Celsius, you're going to form ethene, CH2, like that, plus water. So with this kind of reaction, we are saying that water is being lost. So this water is lost. So what do we call such a reaction? We call it a dehydration. Dehydration reaction. So that's how our dehydration reaction is. And usually marks are given those conditions there. Concentrated or conc sulfuric acid. Then mechanism. Our mechanism. So our mechanism is going to be that concentrated sulfuric acid. First, it's going to dissociate in this form. So concentrated sulfuric acid is going to dissociate, giving us hydrogen ions and hydrogen sulfate ions, like that. So after that, we are going to have the hydrogen attacking our alcohol. So my alcohol, ethanol, oxygen has lone pairs of electrons there. So those electrons are going to the alcohol is going to attack the hydrogen ion using those lone pairs of electrons. Remember from physics, like repels like and unlike attracts. So these electrons at this point, those electrons, we know very well that electrons are negatively charged and protons, all these hydrogen ions, now positively charged. So there is an attraction there, and that's what you're going to base on. So from this, I'm going to be forming CH3, CH2, then O, H2, and a plus. Why am I indicating this plus here? It's because when you look at oxygen is capable of sustaining only two bonds, like in water. So for example, in water, oxygen is of this structure. But now if you add on another bond that is going to be bonded to carbon, this carbon there, you find out that it's now the oxygen is now bonded to 3 atoms, to three to three atoms, hydrogen, and carbon, using 3 bonds. So this oxygen is going to, because of those excess bonds around it, it's going to obtain a positive charge there. So when it obtains a positive charge there, this is what happens next. We are going to break off that this water, because this one has to form water. You remember very well, in our reaction we have water included somewhere here as lost water. So this is the water that is going to be lost there. So how are we going to remove this water? This is what is going to happen. The water is going to be lost. You indicate negative there, in meaning it's loss of water. Then our remaining compound is going to be CH3 CH2 plus. You seeing that? So this carbon atom is obtaining a plus charge there, so we call it a carbocation, and this one is a primary carbocation, or carbocation. Some people call it a carbocation, primary carbocation. It's all the same. So from what I'm having there, CH3, I'm now going to try to expand this primary carbocation in this form. It's going to be CH2 and the hydrogen there. I'm preparing it to lose that hydrogen. So the carbocation here. After that, I'm going to use the remaining hydrogen sulfate to attack this hydrogen here. So the remaining hydrogen sulfate is of this kind. We know from what I'm having here, hydrogen sulfate, you may wonder how I'm manipulating it, but this is it. It has 4 oxygen atoms and 1 sulfur, 1 oxygen. Hydrogens, we don't have a hydrogen atom here. So this is it. So when you try to draw the structure of this hydrogen sulfate, it's going to be bonded to 1, 2, 3, 4 oxygen atoms. Then oxygen, we know very well that it takes a maximum of 2. So it's going to be 1, 2, 3, 4, 5, 6. But we know the other thing you have to know is that sulfur can only tolerate giving out 6 electrons for bonding. So it can only tolerate that for bonding, 6 only. So when I'm drawing this structure, I'm seeing that it's 1, 2, 3, 4, 5, 6. Then this hydrogen is here. Then this negative is taken up by that oxygen. So are you saying that from that oxygen atom having the negative, this is it. Then the remaining part, so the remaining part is this. I think I've tried to bring it out. So from that, from this, let me try to compress this. This explanation is good, so I don't want to rub it. I'm going to minimize it somewhere there, like that. I'll put it in the corner there. That explanation is good, but it's not part of our mechanism. Our mechanism has so I've tried to explain where this negative, that 0, where it's coming in from. Then this negative, those electrons on the oxygen are going to attack the hydrogen. Now as they attack the hydrogen, we're going to break that bond and give back the electrons to make a double bond there. So this is what happens. We remain with C2, H2C. We had a single bond there, but now this arrow, that arrow there has brought a double bond, then CH2, like that. So you see that as the hydrogen sulfate takes the hydrogen, it forms back our sulfuric acid. It's the reason as why they say, or it's stated in science, that a catalyst is not consumed in the reaction. Why? The concentration of the catalyst at the initial stage of the reaction is equal to the concentration of that catalyst at the end. So the sulfuric acid we used here is the same sulfuric acid that is formed back. So that is it. So that one was our primary alcohol. Then I move on to another kind of alcohol. So you can be given some intimidating structure in the question. They will tell you maybe synthesize an alkene from such an alcohol. This one's a cyclo alcohol. So this one is it's like benzene, but it's not benzene. What is it? It's a cyclohexanol. It's coming from cyclohexane. Hex means 6. So cyclo, it's circular. So cyclohexane. Cyclohexane is the alkane. So when I want to generate the alcohol, I just call it cyclohexanol. I think so. I'm removing this N and replacing it with that. So I will minimize this also. So this is what you're going to do with this. I'm going to leave the mechanism for you people. What I want you to see is the reaction: concentrated sulfuric acid at 180, giving us that so plus water. Don't forget that water. So I want to make research about this. Make research about that and the mechanism. So I'm going to move on to I'm going to move on to this. This one is a bit unique. I need to talk about it. So this one is my first scenario. Then this one is the second scenario. Then the third scenario is going to be for butanol. Or butane 1 or 2 CH2 CH2 OH, like that. So when I put in conc sulfuric acid at 108, surprisingly I end up with CH3 C double bond C H2 CH3 plus water plus water there. Don't forget that hydrogen. How is this coming about? Someone may think that it's going to be CH3 CH2. This is wrong, though it seems correct, but it's wrong. So this one is a bit unique. It's not like other alcohols. For sure it's a primary alcohol and it would give us a normal alkene, but for it has a unique component. So first we deal with our mechanism. We have sulfuric acid, sulfuric acid there, dissociating to give us hydrogen and hydrogen sulfate. Then we have the hydrogen attacking the alcohol, CH3, CH2, 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 OH. So it's going to attack those lone pairs of electrons, giving us CH3, CH2, 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 OH2, like that. Now, let me include the bond OH2 plus. So, at this point, we have to remove that water. We have to remove the water. So as you remove the water, indicate that you've lost the water and you have a carbocation, CH2, CH2, CH2 plus 1, 2, 3, 4. Yeah. Then, what makes it unique is that there is a hydrogen shift. After the hydrogen shift, we get CH3, CH2, CH3, like that. We've shifted one hydrogen from this carbon atom to that carbon atom. So it's now complete 3. This one has 2. This one is now having 1. Yet it added 2. It added 2 there. So after this, I'm going to arrange it in a way that I prepare one hydrogen to leave the compound, and usually never tamper with the hydrogen outside. No. You have to get the hydrogen that is within. So I'm having hydrogen there and hydrogen and CH3. So this one has a positive charge there. Then I bring my hydrogen sulfate, and the electrons are going to attack the hydrogen. As you attack that hydrogen, electrons there are going to join that bond to form a double bond. So this gives me CH3, CH, double bond, CH3. So what makes this unique is this shift there. So that, and marks are usually awarded on those reaction steps there, showing the attack, the loss, that attack there, and the end result. So we move on to the next. We have dehydration of alcohols. So we have this we have to note that dehydration becomes more easier, or requires, when I say easier, it's like it requires less energy to dehydrate a tertiary alcohol compared to a primary alcohol. So take note of that. So an example of a tertiary alcohol is this. Don't worry, we shall cover that part of alcohols, and all these things are going to make sense. For now, just look and try to grasp as much as you can. So that one is a tertiary alcohol. Why do we call it tertiary? It's having 3 alkyl groups attached to the carbon atom, the central carbon atom, this one, with the carbon atom that is having the function group. So when you cover function groups, you will understand that the function group here is that hydroxyl ion, or the hydroxyl group. So it's a tertiary alcohol because it is having 3. And I was calling this one a primary alcohol because it's only having one alkyl group attached to the carbon atom that is having the function group. So let me try to have it here. So when you put in when you're dealing with tertiary alcohols, you can either use excess concentrated phosphoric acid and heat, or you continue with your sulfuric acid. But for consistency, let us first go with sulfuric acid. I don't want to confuse anyone. So, but you should be flexible. No, for flexibility, let me put there, because it's what James Kaira has, Demystifying Organic. It's the book we're going to be using. After mastering things there, then we shall move on to Municipal, Ramsden, like that. So, excess concentrated phosphoric acid gives us our alkene of that kind, CH2, this is CH3 plus water. How did it happen? We chose 1 because I'm having 1, 2, 3 and 1, 2, 3. So when I eliminated this and formed the water, we got 1 hydrogen atom from this upper carbon atom. So today we've sacrificed this carbon atom and removed only 1. We removed only 1 hydrogen, such that this is what happened. You may get confused. This is what happened. We have this alcohol, CH3. We have 3 of them. When I put that 3, I'm meaning that it's this and that. So we have 3 of them, carbon, having the OH group. Then this one is going to attack, because we have lone pairs of electrons there. It's going to attack one hydrogen that is bonded to the phosphoric acid. So this one's having a negative charge there, positive charge there. So we have our lone pairs of electrons attacking that hydrogen and forming CH3, 3C, and OH2. I think that now this hydrogen is added to that, forming OH2. Now, as we form this OH2, we've left what was phosphoric acid is now hydrogen phosphate or dihydrogen phosphate. Now, after getting this, remember we have a positive charge there. So, with this positive charge, it's going to be 3C OH2 plus, and it's going to undergo partial ionization or dissociation. So this shows that the reaction is reversible. CH3 plus 3C plus water. What has happened? We've lost the water there. After losing the water, we arrange the remaining product, this one. Try to arrange it such that it's CH3, CH3, CH2, and the hydrogen there. So our hydrogen phosphate is going to do the work, and it's going to attack the hydrogen. As it attacks the hydrogen, electrons are going to be given up to make a double bond there. So CH3, CH3. Now this one was a single bond. There are now two bonds there, and our phosphoric acid is re-synthesized or remanufactured, such that we still maintain that principle of catalysts. So that is it. Then we have I was still looking at dehydration of alcohols. So from dehydration of alcohols, we move on to dehydrohalogenation. So we call it dehydrohalogenation of halohydrocarbons. Sometimes they're called halohydrocarbons. Sometimes you call them halogeno alkenes. They have that halogen bonded to them. So from this, you're going to find out that an example we may have is CH3 CHBr CH3. So from our example, in dehydrohalogenation, as you hear that word dehydro, we are removing hydrogen and we are removing that halogenal group, this bromine. So what do? You apply excess potassium hydroxide and an alcohol like ethanol is more popular. Then you heat. What happens? We are forming CH3 CH2 plus HBr. So what do we call this? We call it first it's 1, 2, 3. So a compound with 3 carbon atoms, if it's an alkane, it's propane. If it's an alkene, it's propene. By the way, we didn't name this alkane here. What's the name of this alkane? First, identify the longer chain. The longer chain is this, and this is the side branch. So start positioning the side branch. But when you're positioning the side branch, according to IUPAC rules, make sure that the function group, which is the carbon-to-carbon double bond, takes the least position possible. So what am I going to do? I'm going to say that if I start naming from this side, it's going to be 1, 2, 3. Are you seeing that? So when I start naming from this side, it's going to be 1, 2, 3. So at this, from this upper, if student A uses that, then student B uses this. I'm saying that the function group for student A is taking position 1, which is the least. Then for student B, the function group is taking position 2. So 2 is greater than 1. Therefore, student A is more correct. So what are we going to say? We are going to give this methyl position 2. So it's going to be 2 methyl. Remember, it's methyl. This is the methyl group. So 2 methyl. The parent chain is prop. But now I'm not going to say it's propane. No, that one is an alkane. I'm going to allocate the position for the function group. So it will be prop 1 in, like that. So that one is the IUPAC name. So in your revision, dedicate time and read through IUPAC names. Try to grasp them and learn how these IUPAC names are generated. Learn how they are generated. First, you consider the function group and its position. Next, consider if it's having maybe a side chain. Then look at that side chain and give it position with respect to the position of the function group. So those are the things you have to take note there. So mechanism. Our mechanism. And in our mechanism, I'm going to have the alcohol reacting with, first it's the alcohol reacting with potassium hydroxide there. So it's going to be potassium hydroxide plus CH3, CH2, which is ethanol, giving us CH3, CH2, or minus potassium plus water. So how would we call this? Potassium potassium okay, it's going to be potassium ethoxide. Potassium ethoxide. The ethoxide is this. That's the ethoxide ion. So we have methoxide, we have, there are very many. So you can generate it from the hydroxide. Hydroxide is HO, then methoxide, then ethoxide, like that. But after generating that potassium ethoxide is going to give in that potassium. So it's going to give in CH3, CH2, or minus plus potassium. Then after getting this, we are going to now attack the main reactant there. So our main reactant is CH3, C, bromine, then CH3. So this one is going to partially ionize, or it's going to break off that halogen. So this reaction is reversible. So when this halogen breaks off due to its high electronegativity, it gains a negative charge there. Then after that, we prepare to lose the hydrogen. So C plus hydrogen bonded to C, H2, and the hydrogen there. So when you look at this, remember we've prepared our ethoxide ion now. This one is now the ethoxide. So the ethoxide is going to attack. So it's going to be O minus CH2 CH3. So it's going to attack this hydrogen as that breaks off there. So it's going to be CH3 C double bond CH2. Don't forget that hydrogen there. So that is it. After this, the bromine ion that has broken off is going to react with the potassium that was generated. So potassium ion plus the bromide ion, giving us potassium bromide, like that. So you're going to try out very many reactions. Let me give you one here. So this one's like your exercise. You try out this. The shape shouldn't intimidate you. Benzene bonded to carbon, chlorine, CH2, CH3, and the 2 there. So it's going to give us, when you add in CH3, CH2, or then potassium and the ethanol, and heat, we form C, CH3, CH2 plus potassium chloride. So you will generate the mechanism. But what you have to know is, for this case, for this question, we were given excess potassium hydroxide and ether, and we used that to form the potassium ethoxide and water. But for this case here, it's like they have prepared for us the potassium ethoxide. So we're only given potassium ethoxide and ether. So what you start with isn't this reaction. Already they have dealt with that reaction, and we are given this. So it means that I'm going to only have trouble in dissociating this, the potassium ethoxide. What I'm meaning, begin with this reaction here. That reaction there is what you begin with. Don't again go back to that. Don't go back to that. So that is it. After, we move on to how do we prepare alkenes from alkynes. So our C from alkynes. So what we are going to do is an example of an alkyne we have here is that CH3 C CH adding hydrogen and Lindler catalyst. So when you add hydrogen using Lindler's catalyst, you get CH3 CH double bond CH2 like that. Then you may have a more intimidating structure of benzene. This structure should be in the right state. Then C triple bond like that. It's going to have hydrogen and Lindler catalyst, giving us C double bond CH2 H like that. So then our part D, this one has no mechanism. For now, it's having no mechanism. Then our synthesis D, remember we are trying to synthesize alkenes from alkynes. So I'm having dehalogenation of vicinal dihalides. So I'm having dehalogenation of vicinal dihalides. So vicinal dihalides are alkyl halides in which the halogen atoms are attached to the adjacent carbon atoms. This is what I mean. An example is the CH3. Okay, let me say CH2 2 bromine. At this point, I think you're all well conversant with this word halide. If it's di, then there are two halides. So that is it. 2 there. So how do we prepare alkenes from vicinodihalides? Just put in zinc and heat. It's going to give us CH2 double bond CH, CH2 there. So you may have another one which is maybe CH3, CH2, CH, maybe chlorine, then CH2, chlorine. So this one, you apply your zinc and heat, it's going to give you CH3, CH2, C, CH2, and the hydrogen there. What are we doing? We are establishing a bond here. As we break off this chlorine and chlorine atom, we establish a bond between those two carbon atoms, and those bonds are we generate a double bond there. So that is it. So don't forget that zinc and the condition heat. So that is for the preparations. We move on to the chemical properties of alkenes, of our reactions. Reactions. So one of the reactions you're having, at least alkenes are more reactive than alkenes. Alkenes are saturated. So what you have to note here that alkenes are saturated, but alkenes are unsaturated. So always unsaturated compounds are going to have a higher reactivity compared to the saturated ones. So that is the case with our alkenes here. So the first reaction we study is halogenation. You remember that we formed the alkenes through the hydrohalogenation. So we are going to see how alkenes react through halogenation. CH3, CH, double bond, CH2, chlorine 2, carbon tetrachloride, giving us CH3, CH, CH2. So this carbon atom takes the chlorine there, and this carbon atom also takes the chlorine. So how do we call it? We call it 1,2-dichloropropane. Propane, because when you look at the parent chain, it has 3 carbon atoms. So we give it 1 to dichloropropane. Dichloro because the chlorine atoms are 2. Propane because that one, the parent chain has 1 to 3 carbon atoms. And this 1, 2, that one is the position of these 2 chlorine atoms. Position. Try to pick that position that gives them the least position possible, or the least number. If someone starts counting from this side 1, 2, 3, you may end up with 2, 3 dichloropropane. 2 and 3, when you add them, it gives you 5. But when you start counting from this side, 1 carbon atom, 2 carbon atoms, 3, you find out that we have one chlorine atom is at position 1. Then the second chlorine atom is at position 2. So it's 1, 2. One is located at 1. The second is located at the second carbon atom. So it's 1, 2 dichloropropane. And mechanism. The mechanism is a bit short. Mechanism. So under the mechanisms, we have CH3, CH double bond. Alkenes are having double bonds, and it's this double bond that goes on to attack the chlorine. Remember, the chlorine molecules are always having 2 atoms within them. And due to high negativity or negativities, 1 chlorine atom is going to withdraw some of the bonding electrons towards itself, such that it makes this one partially positive. As for it, it's this side is partially negative. So what happens is that after attacking this partially positive chlorine atom, electrons are going to be given to this the one that is partially positive, such that as the reaction progresses, we have CH3, CH. Then the other thing you have to note is that the first chlorine atom to attack is going to be added to the carbon atom with the highest number of hydrogen atoms. So this is what I mean. This carbon atom has 2 hydrogens. This carbon atom has 1 hydrogen. So the one with 2 is given the chlorine. Then this one is left with a positive charge there. Why is it having a positive charge? Because it's not fully bonded. This is it. It is bonded to hydrogen. No. It's bonded to hydrogen. Then one is bonded to the other carbon atom there. Then the other bonded to the carbon atom this way and that way. So we are lacking the 4th bond. So we give it a positive charge there. So after that, we move on to resolving that, because our compound is not stable with that carbocation. So what we do, bring this chlorine. By the way, as we give in this, it's going to, we lose that chlorine there. So it's the same chlorine that is going to come and attack is positive. Remember, positive and negative are always in association in our reactions. So it's going to give us CH3, CH, and there the chlorine, CH2, and the chlorine there. So that is it. So I'm going to leave you with this. A double bond there, and the CH3. When we add in bromine and the carbon tetrachloride, what do we form and the mechanism? You can pause the video and work out that number there. So I'm moving on to this, and this is, by the way, this one is needed. It's practical. It's a chemical reaction, but it's practically examined. Addition of bromine water. Oh, yeah, bromine water. You may be told to state what is observed, maybe before I even go to this practical part of it. When you add an alkene to bromine, there are certain observations you have to take note. So, maybe, for example, let me use this example. If I'm having a simple alkene, like ethene, when I add in bromine, so well, you know very well bromine is reddish brown. So when I add in bromine here and the carbon tetrachloride, this carbon tetrachloride is just a solvent. We saw it. So it's going to give me CH2, C, bromine, CH2, bromine. Now, when you look at this, I've used the simple alkene to represent very many alkenes. So, when you add in bromine, what is the observation? Maybe when you're in the laboratory and you try out this experiment, and they tell you maybe write the observations. What are the observations here? You're going to state that since bromine is brown, the reddish brown solution turns colorless. It's going to turn colorless like that. How? This is reddish brown or brown, and this one is colorless. it means that when I add bromine into any alkene, the color changes. The color automatically changes. So we move on to addition of bromine water. So addition of bromine water or chlorine water. So when I add bromine water to any alkene, this is what happens. Maybe our simple alkene, which is ethene, adding bromine water, it's going to give us CH2, bromine there and bromine there, plus hydrogen bromide. So what are the observations? This one is reddish brown, turning colorless. So when you look at these two observations, they're kind of similar. Bromine water or bromine liquid, they give the same observations, reddish brown to colorless. And this test is a test for unsaturation. So when you see such color changes happening, you understand that one of these is an unsaturated compound, or the reactant is unsaturated. It has a double bond. So mechanism. So our mechanism is going to be we are going to have two hydrogens bonded to carbon like this. So at first our bromine is going to present itself in this form, and this one is partially negative, partial positive. Why? Because this one is withdrawing that bromine there is withdrawing the bonding electrons to itself, attaining that negative charge, leaving this one partially positive. That's why we show it that way. Then after you show the attack by this arrow, as the reaction takes place, we break off this bromine and indicate it there that we've lost. This arrow behind shows the loss, and this arrow here shows the charge. So don't be confused by the two. So as the thing proceeds, we have CH2, CH2, bromine binds to that, and this gains a positive charge, such that at this very point, remember we have water there, and water is in plenty. So the water is in plenty. What it does, this water has carbon and has oxygen, and this oxygen has lone pairs of electrons. So when these lone pairs of electrons sense a positive charge on carbon, it causes our water molecule to attack like that. Now as it attacks, we have this compound formed. Remember, oxygen can only support 2 atoms bonded to it now, but for now I'm saying 3 bonds, yet it can only support how many bonds? It can only support 2 bonds. So this is H2 and bromine there. So what it does, it obtains a partial positive charge. How do we neutralize this charge? We have to break off 1 hydrogen. Cut it. As we break off that hydrogen, we show that we've lost it. Then we form H2, C, OH, H2, C, OH, CH2, and bromine there. So this is it. What is it for now? So we move on to reactions with hydrogen halides. Reactions with, it will be my part C. So reaction with hydrogen halides, like that. X stands for any halide, any halogen. So I'm going to move straight to the reactions, and my first reaction is going to be this simple ethene, and when you add in hydrogen bromide in its gaseous state, when it's dry, when you add it there, it gives you CH3, then CH2, and bromine there. So if I'm having maybe CH3, C, H, double bond CH2, and I add in maybe hydrogen bromide gas, when it's dry, it gives me CH3, CH, CH3, and bromine there. So what happens? This hydrogen goes to the carbon atom with the maximum, or with the higher number of carbon atom, of hydrogen atoms. So what am I considering? I'm considering these 2 carbon atoms, those 2, the ones that are having the double bond there, or the function group. So of these two, the one having a higher number of hydrogen atoms is what I'm going to consider, and I'm going to give it the hydrogen. That's why when you look here, it was 2, there are 3. Now the remaining one, I give it the bromine. So in the mechanism, it's going to be CH3, C. I'm going to spread this a bit, CH2. Then I'm having hydrogen and bonded to bromine. We know very well that these halogens are having a higher electron affinity. So it withdraws electrons from hydrogen, making hydrogen partially positive, and for it gains that negative charge there. So as these electrons are being withdrawn, we attack using our double bond. Now as we attack the hydrogen, that hydrogen is going to be added to, so that hydrogen is going to be added to that last carbon atom with 2 hydrogens, and I remain with a positive charge. Now as I remain with a positive charge, remember this bromine is breaking off, giving me loss of the bromide ion. So the bromide ion is going to use these excess electrons to attack. Now as it attacks, it's going to give us CH3, CH, bromine there, so it's going to be CH3, CH, bromine, and CH3, like that. So what am I following with this mechanism? I'm following what we call Markovnikov's rule. And in Markovnikov's rule, we stated that the carbon atom that is sharing the function group with another, but that carbon atom with the highest number of hydrogen atoms is the carbon atom that will take the hydrogen from the hydrogen bromide, like that. So that is it. Then we move on to, I've called this, I'm following Markovnikov's rule. Markovnikov's rule. Now we have to study the anti Markovnikov's rule and see what does it state. And within this anti-Markovnikov's rule, this is what happens. If I'm having maybe maybe CH3, CH2, CH2, like that. Then I add in hydrogen bromide there, and I add in an organic peroxide. So organic peroxide. It's going to give me CH3 CH3 it gives us CH. Now the difference with antimechanical rule is like when you that's true, but in antimechanical rule, remember in Markov's rule we said the hydrogen goes to the carbon atom with the highest number of hydrogen atoms. But now for this one, it's going to get this hydrogen. In antimechanical, we get that hydrogen and give it the one having the least number of hydrogen atoms. Then this bromine, we give it that carbon atom with the highest. So we end up with bromine being there and the 2 hydrogen atoms there. So that is it. Then so we move on to we've seen that one having an organic peroxide reaction with sulfuric acid, sulfonation. So reaction with sulfuric acid. So from this, maybe if I'm having CH3, CH, double bond CH2, and I add in concentrated sulfuric acid, and our temperature will be 15 degrees Celsius. It's going to give us CH3, CH3, and O, SO3H, like that. So what is the mechanism? So in our mechanism, we are going to have CH3, CH, double bond CH2, and that double bond is going to attack the hydrogen and the hydrogen on sulfuric acid, such that as we attack the hydrogen, bonding electrons are going to be returned to oxygen, and this is what we're going to form: CH3, C, and C, H, C, H3, like that. So that is what is going to happen. But as we as we break off this hydrogen sulfate, this hydrogen sulfate is reactive and it's going to attack this positive carbon atom, forming as it breaks off, it's going to form CH3, CH3, O, SO3H, like that, such that that positive charge is neutralized. So hope you're getting it. Then we have a reaction like reaction with water, acidified water. So reaction with, this one was reaction with the sulfuric acid. Then I'm having a reaction with acidified water, How is it going to be? It's maybe we use CH3, CH double bond, CH2, that is propene. Add there hydrogen ions and water and warm. When you warm, it gives you CH3, CH3, and this carbon atom gets the OH there. So it's like you're preparing an alcohol, but this alcohol is propan 1 or propan 2 or by the way. Propan 2 or is the reaction is the product we have there. So the mechanism. In our mechanism, you're going to use that hydrogen there to attack. So for the mechanism, it's going to be CH3, CH double bond, CH2, and this is going to attack the hydrogen there. Then we form CH3, positive charge there. Then we have our water, H2O, and this water has lone pairs of electrons. So this water is going to attack that carbon atom, giving us CH3, CHO, H, positive charge, then CH3 like that. After, we have to neutralize this charge by breaking off one hydrogen, such that we use the electrons it was using for bonding, at least we use them for neutralizing that charge. So we lose the hydrogen here and form CH3, CHOH, CH3, like that. So that alcohol is there, and that is the mechanism. Then we have reactions with alkaline potassium, manganate 7 solution. So we have reactions with alkaline potassium permanganate, reaction with alkaline potassium manganate 7 like that. So how is it going to be? I'm going to use this example, the simplest. CH, it's H2, C, double bond there, C, H2, and potassium manganate 7 aqueous. Then add in OH there. What does it give you? It gives you a diol. A diol. So CH2, CH2, this is OH, and the HO, like that. So this one is called ethane 1,2 diol, like that. Ethane 1,2 diol. So you look for more. This one has no mechanism. You look for more reactions falling there. Then we are having a reaction with acidified. So take note, this is alkaline because of this, because of that OH there. It's alkaline because of that OH. But now this one is going to be acidified. Acidified potassium manganate 7 solution. So our main emphasis is there on acidified. And an example I'm going to use is this. I'm going to use CH2. When I add in potassium manganate 7 aqueous, and I add in an acid and I heat. Remember this one you heat, this one you don't heat for the alkaline, but for the acidified, apply some heat there. So what it does, it's going to break this in the middle, and the product is going to be 2 carboxylic acids. So one is this carbon atom it's going to get 2 OH, 2 oxygen atoms. Then you see that if you try to look at it keenly, there are 2 hydrogens. So 1, 2. Then we give it 2 oxygen atoms. Then there is this one also. That one is also going to get. So you see that these 2 are similar. And if they are similar, I have the right of putting there 2 and rubbing off this, such that I form 2 carboxylic acids. So after that, we have ozonolysis as a reaction there. So ozonolysis. And under ozonolysis, if I have my alkene of this kind, so if I have my alkene maybe of CH3, CH2, no, double bond, CH3, when I add in ozone and carbon tetrachloride as our solvent, then at a temperature of 20 degrees Celsius, it gives me an ozonide, CH3, CH, O, CH, CH3, then one oxygen there. So this one's called an ozonide. So this is an ozonide, like that. Then when I add zinc dust, and ethanoic acid to this ozonide, I'm going to get when I add ethanoic acid and zinc dust, I'm going to split it into two. It's going to split into two, like that, and we shall form two carbonyl compounds. See, double bond O, like that. But since the carbon atoms this side are equal to the carbon atoms that side, I'm going to give it a 2 there, because we are forming two carbonyl compounds that are similar. That is, which is our ethanol. So that is it. Then when we move on to hydrogenation of alkenes, so hydrogenation, and in hydrogenation, as you hear that word hydrogen, it's going to be, I'm going to insist on this one. It's simple. So when you go into your revision, you will build on this. It's a good start. It's going to give you a good start. So when I add in hydrogen nickel catalyst at 150 degrees Celsius, I'm turning this alkene into an alkane by adding hydrogen atoms on it. So as I add hydrogen atoms on it, it becomes an alkane, from an alkane to an alkane. Then the other reactions that I'm not going to stress on are combustion. So first, let us first master the 80% Let us first master the 80%. Then we shall come back for the 20% when we've mastered the other ones. So how do I identify existence of a double bond? I will call it test lab test. Then in our lab test, this is what is going to happen. If you want to test for presence of a double bond, I mentioned it earlier, use bromine. When you use bromine, it's going to give you, in carbon tetrachloride as a solvent, you're going to get your halogenoalkane, which is racino dihalide, but now this one is colorless. Color, it's colorless. And if that one is colorless there, and yet this side it was brown or reddish brown, your observation will be the reagent or reddish brown solution turns colorless, and the conclusion will be alkene detected or alkene present. So then the other thing you have to at least look into are the uses of alkenes. And one of the uses of these alkenes is in polymerization, and in making of plastics. So ethane is used in making plastics. So like polythene, polychloroethene. Then ethane can also be used to make ethanol. So this ethane is used to make ethanol. We saw that reaction where we were reacting alkenes with acidified water, and we ended up with non-alcohol. Then propane is also used in the manufacture of propane, propan-to-ol, and phenol. So this ethane is used in synthesis of phenol. How? So you have to turn from ethane to ethine, then to benzene, then you move to phenol, like that. So that was our topic. That was our topic from Job's Kaira text. That book of Job's Kaira. So this is the end. And next we have alkynes. So I think you should take a look at this. Try to take screenshots, or you can have access to this work, or you read that direct text book or that book of James Kaida. But with this video or with this recording, I think things are going to be easy for you to understand. Things are not going to be new.